Hello, in this video we're going to look at an example where we want to find a basis for the solution space for the following system of equations. So if we put these equations into our augmented matrix, so this gives us 1, -2, 1, 0, second equation, -1, 2, -1, 0, and the last 3, -6, 3, and 0. If we put this in reduced row echelon form, what we find is that we get a matrix with two rows of zeros. So we get the top row 1, -2, and 1, and then the second and third row are all zeros. Notice that in this system we have one leading 1, which suggests that we will have a leading variable for x. Okay, so y and z will be free variables. X will be a leading variable. So let's take a look at what the equation we get from this first row is. So the first equation, or the only equation we get, is x minus 2y plus 1z equals 0. And the other rows of zeros don't give us much information. Now, we said that x is the leading variable, so we want to solve for x. So we get x equals 2y minus z. And that's helpful, but that's not really a good representation of the solution. What we want is we want to write x equals, y equals, and z equals, right? We want to present what the solution is. Now, since y and t are free variables, let's call those t and r. You could choose any parameters that you like. And then for x, our leading variable, we know that's 2y minus z, or we could say a 2t minus r. Okay, so let's write this. We have our solution to the system. We could write it as a vector. Vector x, y, z is equal to 2t minus r, t, and r. In other words, the solution looks like linear combinations. Let's see, t times some vector plus r times some vectors. The solution looks like a linear combination of two vectors. In the vector we're multiplying by t, we should only have a 2, 1, 0. And in the vector that gets multiplied by r, we need a -1, 0, 1. In other words, the span of the solution, so let's write this down, is given by these two vectors. In other words, the two vectors 2, 1, 0 and -1, 0, 1. Those two vectors span the solution, or the span of those two vectors is the solution space. There's a lot of ways to say that. Okay, let me write that a couple of different ways so that we're comfortable with the language. So that equals a solution space, and let's give that solution space a better name. Let's call it W so we can start referring to the space. So W equals the set of linear combinations of these two vectors. That's one way to say it, where t and r are real numbers. We can also say W is equal to the span of these two vectors, which is what we have up above. Okay, so those are equivalent ways of writing the same information. So what we're really interested in is we're interested in a basis for W. So let's write that down, a basis for W. And remember, to be a basis, we have to span W. And the vectors have to be linearly independent. So already for condition 1, we know that these two vectors, their span is equal to W. So those two vectors do span all of W. The next thing we need to check is linear independence. So let's check for linear independence. We need to check if C1 times 2, 1, 0 plus a C2 times -1, 0, 1. If those give us the 0 vector, does that force C1 and C2 equal to 0. So if we work through this, we get a 2C1, 1C1, and a 0C1. We get a negative 1C2, 0C2, and a 1C2 equals 0, 0, 0. And now doing vector addition, we get 2C1 minus 1C2 for our first component. Second component, 1C1 plus a 0C2. And the third component, 0C1 plus a 1C2, and that's supposed to equal 0, 0, 0. So if we equate the first components with each other, we get an equation 2C1 minus 1C1, minus 1C2 equals 0. And now if we equate the second components, we get another equation. So we get 1C1 plus a 0C2 equals 0. And that's for our second components. If we equate those. And if we equate the third component, similarly, we should get another equation. And let's put that in a different color. So third components. The bottom line is, if we're really checking for linear independence, the thing that we need to do is we need to look at this augmented matrix with column vectors 2, 1, 0, negative 1, 0, 1. And we need to perform elementary row operations to see what we can learn about C1 and C2. And once we do that, we get the following, which implies that C1 equals 0 and C2 equals 0, and this says that our two vectors are linearly independent. So going back up here to our check, yes indeed they are linearly independent. So we have found a basis for W. So let's wrap this up. So basis for W, and recall W we said was our solution space. We'll see later on that the space of solutions for homogeneous systems always form a subspace. But for now we'll take it as given. So basis for W, it is the set of vectors 2, 1, 0 and a negative 1, 0, 1. And from that we could add, since there are two elements in the basis, that means that the dimension of W, is 2. In other words, W is a two-dimensional subspace. Is a 2D subspace of R3. And 2D subspaces, those look like planes.